Hello everyone, my name is Flavio Arrais and I'm going to talk about a fire design proposal for members with cold form and lipid channel and sigma sections under compression, a research work performed at the University of Aveiro. During this presentation, I'm going to focus in the following topics, starting with a small introduction with concepts about cold formed steel profiles under fire. Then I will present the current fire design rules and the new proposal as a result of this study. About numerical study, I will detail the numerical models development according to the different case study analyzed. A parametric study is going to be presented with some numerical results obtained and the comparison with the mentioned design rules and with a statistical analysis. And finally, the global conclusions about this work to finish the presentation. Starting with introduction, cold-formed profiles are used due to their lightness and ability to support large spans. Currently, there are several applications of these profiles on roofs or walls support elements in different building types, such as shopping centers, industrial buildings, structural repair and rehabilitation, residential buildings, offices, and sports stadiums. Its application is quite common in buildings with a high occupancy rate, which have higher fire resistance requirements due to the greater risk of human losses. Once the steel has a high thermal conductivity when subjected to high temperatures, mechanical properties start to deteriorate from a certain moment, leading to a loss of strength and stiffness, which means that we have to consider the reduction factors of the Young's modulus and proportional limit strength. These profiles present specific characteristics which lead to local, distortional, and global buckling phenomena occurrence. At elevated temperature, these instability phenomena are intensified, which means that they should be considered on the fire resistance evaluation. This research is about the behavior of simply supported columns with cold-formed steel lipid channel and sigma cross sections in case of fire. Different parameters like the slenderness, steel grades, and elevated temperatures were considered. With the Sapphire finite element software, the fire resistance of cold-formed steel lipid channel columns were numerically obtained, and the buckling mode shapes obtained with the software CAST3M were used to define the numerical model's geometric imperfections. Presenting the different design rules considered and analyzed. According to Part 1.2 of Eurocode 3, the design buckling resistance of a cold-formed steel member of class 4 cross-section subjected to compression, considering the lateral buckling, should be verified by satisfying this expression. However, the French National Annex from the same part of the Eurocode 3 presents a similar expression with considering a constant imperfection factor. The effective cross-section was obtained according to the Part 1.3 from the same Eurocode by the local instability mode according to the method of the effective width and the distortional instability mode determined by the reduced thickness method. For not doubly symmetrical cross-sections, the actual load will be eccentrically. Therefore, the additional moment should be taken into account. Therefore, these were the equations applied in this work to consider the load eccentricity, and also the correspondent equations from the French National Annex with more simplistic considerations, such as considering all the interaction factors equal to 1, and the constant imperfection factor. Also presents lower reduction factors when compared to the reduction factors from the general Eurocode. Here I presented the different steel constitutive laws according with the respective annex, where the French National Annex presents reduction factors with lower values. As you can see here, in this case for 350, 500, and 600 degrees. This new proposal is based in an adaptation methodology for flexural buckling on cold-formed steel elements, where the equations considered in this new design proposal remain the same from part 1.2 of the Eurocode 3, considering the use of interaction equations with the flexible buckling curve of French National Annex and the new imperfection factor in function of the cross-section shape. In this work, the cross-section resistance was obtained numerically with the Saphir software and considered in the analysis. Now presenting the numerical modeling, conformed steel columns for these 10 different cross-sections, 7 lipid channel and 3 sigma sections, under 3 different height temperatures were considered. The choice of the temperature, 350 degrees, is related to the recommended critical temperature for profiles with class 4 sections when no calculation is made, being the other temperatures chosen for being common critical temperatures in this type of structural elements. Different members' length were also analyzed, with the lengths between 1 and 10 meters, considering this slenderness range. 4 different steel grades, and the uniform temperature was considered. Shell elements with 4 nodes, with each 6 degrees of freedom, 3 translations and 3 rotations, applying the finite element software Saphir, were considered. The mesh was refined at the corners to reproduce the rounded shape, simple supported at the ends. The loads were applied parallel to the member axis at the ends according to the linear stresses distribution presented. This study did not take into account the corner enhancement resulting from the manufacturing process, and only the flexural residual stresses were considered. Geometric imperfections were considered with the buckling mode shapes obtained with the CAST-3M and the Ruby interface. The amplitude of the local, distortional, and global imperfections were 80%, according to the Part 1.5 of the Eurocode 3, from those recommended by Part 4 of EN 1090. The flexural buckling stresses were based on Schaffer and Pecos, according to the diagram presented. Also, according to Part 1.5 of Eurocode 3, to combine these different geometric imperfections, as well as the material imperfections caused by residual stresses, a leading imperfection should be considered, with the total amplitude and the accompanying imperfections with 70% of its value. To validate the numerical models, 12 simple supported columns were considered, heated with the ISO 834 curve. 2 different constitutive laws from the current Eurocode 3 Part 1.2 and from the French National Annex were studied on the numerical analysis, with the conclusion that the French National Annex constitutive law provides a better approximation to the experimental results and also safer results. Now presenting the numerical results obtained with Saphir and the different file design rules. Here 4 different cross-section slenderness are presented. As it is possible to see, the current design rules are conservative. However, the French National Annex presents design curves less conservative or unsafe in some cases, and the new proposal fits better to the numerical results. Varying the temperature, no visible differences are presented between the numerical results, and related to the different design methodologies, the same conclusions are observed. And here the results, considering the different steel grades, the same conclusions are obtained. The influence of the results of different steel grades is visible. Considering a low steel grade, the numerical results are far from the Eurocode 3 rules, being the approximation improved when the steel grade increases. The current Eurocode 3 rules still being over-conservative, but the French National Annex tends to be increasingly insecure for the results. The new proposal balances, once again, this difference being often on the safe side, where the unsafe results only occur for the limit range of steel grade. Here is presented the failure mode obtained from the tested columns. For a detailed analysis of the obtained numerical results, a statistical evaluation of the methodology is presented. following the three criteria of the validation procedure proposed by Krupa, it is possible to observe that the current methodology is too conservative without unsafe results. The French National Annex seems to present a better agreement, however, with significant unsafe results for lipid channel columns. The new proposal presents average values closer to 1 and the lower standard deviations, proving to be less conservative and safe at the same time. Finish this presentation, the behavior of double-hinged columns with conformed lipid channel and sigma sections in the case of fire was presented with a parametric numerical study. Lipid channel numerical models were developed for the studied cases and validated against several fire tests from the literature. A comparison between the ultimate numerical loads and the fire design formulae prescribed in the Eurocode 3 was performed. Regarding the column's fire resistance, the current design rules demonstrated to be generally over-conservative. The steel grade affected the resistance of the tested profiles, which is significantly enough to be considered in the calculation formulae. The design rules of the French National Annex were in better agreement with the numerical results. However, too many cases were on the unsafe side. Adjustments to the Eurocode 3 design formulae were proposed as an adaptation of the existing rules covering a high number of cases in a less conservative way while maintaining safety. Different imperfection factors for the lipid channel and sigma sections were proposed. When the imperfection factor depends on the yield strength, it is possible to observe a better agreement with the numerical results of different steel grades. And the numerical results demonstrated the importance of this adjustment, crucial for the Eurocode curve's accuracy. Thank you very much for your attention.